In the past 4 years, the nature of digital radio technology has changed dramatically. High-capacity 3DS3 systems have become available which make digital radio a cost-effective transport facility. Although many of the transmission and reception problems inherent in the early days of digital radio were solved, a lot of us were reluctant to embrace this new but exciting technology. This reaction was in part due to fiber optics. It seemed that the world viewed fiber as the ultimate solution to all transmission facility needs. As one of the largest manufacturers and users of fiber optics, we at AT&T quickly realized that fiber is not feasible nor needed everywhere. Yet the public and you, our customers, demand the quality fiber offers. So we developed digital radio equipment with an error correction system that virtually eliminates errors. We also perfected our protection switching equipment so that it can switch from the working channel to protection without introducing a single bit error. But the question remained, would it be possible to ensure the reception of a quality signal and solve the problem of multipath fading? The answer, I'm happy to say, is yes. Recently, Bell Laboratories has achieved a major breakthrough in microwave reception. It's called an angle diversity antenna. As you will soon see, its performance is far greater than space diversity. And because it involves only one receiving antenna, our customers can minimize tower modifications. But now, I'd like you to see the story of our angle diversity antenna, the wave of the future.
This is the microwave radio station in Brawley, California, in the middle of the Imperial Valley. The signal, sent from a transmitter in Salton, travels over 37 miles of dry, flat desert land, interrupted by patches of irrigated farms. This unique mixture of dry and wet land, combined with the heat and flat terrain, make this one of the most challenging locations for a radio hop anywhere in the world. A team of engineers from AT&T's Bell Laboratories facility in Andover, Massachusetts, have been monitoring the signal received by an unprotected conventional horn antenna. Over a 3-month period, they have recorded almost 20,000 severely errored seconds. Based upon the CCIR objective, that's equal to an incredible 49 years of errors.
We monitor several radios.
At the same time, they have been monitoring another radio being fed by a new microwave antenna system. The system's design is based upon new research in angle diversity conducted by Bell Labs. The results are equally incredible. Angle diversity is a concept that Bell Labs has been aware of for a number of years. But the most recent work, led by Adolf Giger and Ernie Lin, has for the first time successfully addressed the use of angle diversity in line-of-sight microwave radio links. This work is being done at the AT&T Bell Laboratories facility in Andover, Massachusetts. While many people were hailing fiber optics as the wave of the future in communications, the engineers here looked at fiber as an interesting challenge. It offered a goal to strive for, to develop the radio technology that would provide a transmission medium as good as fiber and more cost-effective. To achieve this would mean developing equipment that eliminates bit errors caused by dispersive fading. Equipment able to switch from a poor signal to a good one without introducing errors, and able to maintain lock even when that signal falls far below acceptable levels. Many people thought it would be impossible. Luckily, none of them work here.
Angle diversity had been used successfully in troposcatter communication links. And we know from my previous work, it can be applied to line-of-sight microwave radio links as well to mitigate the problem of multipath fading.
Normally, in line-of-sight radio links, An antenna receives a signal from a transmitter placed about 25 miles away. Often fading occurs when the signal is reflected either from an atmospheric layer or from the ground. Both the direct and the reflected ray reach the receiver out of phase, and this cancels out the signal. Typically, this problem has been addressed by using a second antenna placed below the first. Most of the time, when one of the antenna's signal was bad, the other would be good. Although this worked more often than not, it added considerable expense. It meant not only the addition of another antenna, but quite often costly tower modifications. Bell Labs researchers saw that sufficient diversity could be achieved by using a single antenna with two beams offset in elevation. The two beams, separated by a fixed angle, are created by offsetting the two feeds slightly above and below the focal point of the parabolic antenna. If successful, this would eliminate the costly tower modifications and often allow the use of a shorter tower. According to Bell Labs researchers, if an angle diversity system was properly designed, when the second undesired ray arrives, distorting one of the beams, the second is essentially unaffected, at least on paper.
I showed the results to my boss and told him I'd like to try it out somewhere in the field. He asked me where I'd like to go. I say, how about Hawaii? He said, how about the worst hub in the country?
Hot, static air, flat terrain, and low altitude moisture are the three main causes of refraction in microwave radio transmissions. The Salton Brawley hop has them all. Beginning in June of 1986, AT&T ran a series of field tests on an 8-foot angle diversity antenna built to Bell Labs specifications. The tests compared the regular horn antenna, a space diversity antenna, and the angle diversity antenna. All were feeding single sideband analog radios that had been instrumented by Ernie Lin. Most experiments go on for a year and show a few minutes of fading. At Brawley, the team had several hours of fading in a few weeks, some as severe as 60 dB. The team charted their results in terms of the in-band power difference. In-band power difference is determined by measuring a signal's maximum and minimum amplitude within a particular band. Here is a graph that tracks the accumulative time for various dispersion levels over a 3-month period in terms of the in-band power difference. Line 1 is the main unprotected antenna. Line 2 is the space diversity arrangement. The third line is created by combining the output of the two beams from the angle diversity antenna. From these curves, Ernie estimated 14,000 severely errored seconds for the regular horn antenna. As you can see, the improvement factor between the regular antenna and the space diversity is 100. But with the angle diversity antenna, the improvement is about 1,000 times better. After reporting the preliminary results, the team was provided with AT&T's digital radio, DR6135, by the Network Systems Product Management Organization for the next series of tests. It started as a standard radio, with both a double error correction and error-free switching system unique to the AT&T line. This computer-controlled multipath fade simulator can stress digital equipment the same way nature does. We use it here at Merrimack Valley to test the effectiveness of transversal equalization, error correction, and protection switching equipment in our systems. Here, the simulator is creating a 19 dB static notch in the signal we're receiving. This level of dispersive fading causes a bit error rate of 10 to the minus 6 on the radio line. But with AT&T's double error correction, the digital signal to the end user will be error-free. In this particular example, the protection switch was locked out to verify the performance of the error correction. In the real world, the AT&T system will switch from the working signal to the protection based on the uncorrected error rate of 10 to the minus 6. This is made possible by the errorless switching feature incorporated in frequency and space diversity receivers. Thus, the AT&T digital system effectively bypasses multipath fading without passing a single bit error onto the end user. The combined power of the error correction and errorless protection switch can be demonstrated if we disable the protection switch and increase the fade depth to 21 dB. This is well beyond the capability of the error correction alone. But when we activate the protection switch, the system responds to the challenge, providing high-quality digital transmission instantly. In order to obtain pure results, both the double error correction and the error-free switching system were removed. If they had been left in, we may never have seen an error.
We knew we were on the right track. We had developed a system that could perform better than anybody ever dreamed of. A system that would allow us to build over hubs where previously it was impossible to achieve performance objective. Also, another byproduct is that expensive tower modifications could be avoided.
In the spring of '87, over a 3-month period, more severely errored seconds were compiled than most hops see in 49 years. A total of almost 20,000 seconds from the regular horn antenna. From the space diversity system, they recorded 243. But from angle diversity, they compiled only 19. This is an improvement factor of over 1,000, and this is without any form of error correction. In June, Ernie presented the team's findings to an enthusiastic audience at the International Communication Conference in Seattle, Washington. From there, he returned to Andover and another series of field trials. This series would include another AT&T innovation, a robust receiver developed by Bell Laboratory engineers Martin Myers and Glenn Miller. The robust receiver has the ability to maintain lock during severe fading conditions. Here, a 25 dB fade is sweeping across the channel. This fade depth is beyond the ability of even a 7-tap transversal equalizer. However, as you can see by the square shape of the phase plane, with the robust receiver, synchronization is maintained. As soon as the deep notch leaves the channel is available for use. There is no need to wait for resynchronization because lock was never lost. Another example of the power of the robust receiver can be seen by adding thermal noise to the signal. The receiver maintains synchronization even with the signal-to-noise ratio as low as 5 dB. This corresponds to a flat fade of about 60 dB, a level almost never seen outside of Brawley, California. As the testing continued, the first angle diversity system was installed in Prospect Valley, Colorado. One day, Ernie received a call from one of the team's co-workers.
It looked like something was wrong with the equipment. I asked him what happened. He said he had not received a single error in the last few days. Usually, he would see a few errors. He thought it was more realistic to have equipment failed rather than to have error-free transmission. I told him not to worry about it. That's something he had to learn to live with.
Bell Labs' work in angle diversity, coupled with the unparalleled performance of AT&T's digital radio systems that include double error correction, error-free switching, and the robust receiver, can meet the most stringent performance objectives your customers will ever need. AT&T Network Systems and Bell Laboratories, where the research goes on.
The angle diversity antenna is available now, and it is supported by AT&T's regional organizations that provide assembly, installation, testing, and orientation. Presently, there are 2 angle diversity sites up and working in the AT&T network. 2 others are now being installed for different telephone companies and will be operating in early 1988. What will angle diversity mean for these networks? It means improved quality of microwave reception without the costly tower modifications needed for the space diversity configuration, a cost that can run as high as $10,000 to $25,000 per tower. It also means being able to place towers on rooftops where the necessary vertical clearance for space diversity does not exist. And teamed with the unparalleled performance of AT&T digital radio, it means that you may never see another bit era again. With the angle diversity antenna, digital radio has never sounded so good.